Hi, and welcome to Dr. V's AP Chemistry webcast. The topic for today, spectroscopic methods. We're talking about this because in order to get through the AP Chemistry exam, you do need to have a little bit of knowledge about some analytical techniques and what they're used for. You don't have to go into a great deal of detail here, but what I want to do is introduce some key methods that are part of the AP Chemistry curriculum and talk a little bit about their uses in chemistry. We don't have to go into any great detail here, and so this is not going to be suitable if you're in organic chemistry and you need to know about these methods in great detail. This is just a really brief overview to get you through what you need to know for the AP Chemistry exam. So I'd like to start by talking about microwave spectroscopy. And as you might guess, microwave spectroscopy uses microwave radiation. And what it really focuses on is molecular rotations. Now, in order for microwave spectroscopy to work, you do need to be talking about polar molecules. Microwave spectroscopy gets very complicated and the spectra get very involved, but they do have some real-world applications and they're used a lot in atmospheric chemistry and also in astronomy. There's different applications and, of course, the pure research aspect of that. But at this point for AP Chem, what you need to know, if it's a microwave spectroscopy, it's all about rotations of molecules. Done. All right, I'd like to talk a little bit about infrared spectroscopy, often called IR spectroscopy. And this uses, again, as you might imagine, infrared light to do this. And what it's studying is molecular vibrations. Now, this is used extensively in organic chemistry. It's a really powerful analytical tool because different kinds of functional groups in the molecules vibrate at with different energies. And so the energy it takes to get that vibration going changes. So we can use this to actually identify functional groups that are in the molecule. So it's a really powerful analytical tool that way. All right. There are actually different kinds of vibrations. We can have bending motions, where the molecule is literally bending maybe around a central atom. We can also have stretching motions. So we can have a symmetric stretch where the molecule is both atoms, say, coming off a central atom are stretching the bond like a little spring to the same extent. And we can also have asymmetric stretches where one side is stretching more than the other. You could actually get up and act this out, right? Can you do a bend? Can you do a symmetric stretch? Can you do an asymmetric stretch? And think about the different ways the molecules can be moving. All right, another type of important spectroscopic method is NMR, nuclear magnetic resonance. And this uses radio frequencies. And it's all about nuclear spin. So the spin of certain nuclei, you can get them to align with a magnetic field. The energy it takes to get this to happen, we can measure that. And so it's a way of probing structure of molecules, and it can get really involved. So we can look at molecular structures. So for example, we've got an ethanol sample here, and there are sort of three different situations for hydrogens. And they end up having different amounts of energy to get them to do their thing, and so they show up in the spectra. We don't need to go into any kind of detail with this. You could do a whole course on just these spectroscopic methods. You could spend 6 months to a year studying this. You could spend your whole career studying these different techniques. We just need to know big picture, all right? So it's about nuclear spin, and then we can use that to look at molecular structures, and it can be used for very small molecules. It can be used for very large proteins. There's lots of different applications of NMR, right? The last method I wanted to talk about was UV-Vis spectroscopy, which, as you might imagine, uses ultraviolet and visible light. It depends on electronic transitions. So electrons being in a certain energy level, they absorb energy and jump to a higher energy level, and then they can relax back down to that lower energy level. Again, it does use ultraviolet and visible light, and so we can get an absorption spectrum, what wavelengths of light are involved to get these different electron transitions to happen, right? In order for absorption in the visible region to occur, we're talking about colored species, so that is something that's shown up on the AP Chemistry exam in different forms over the years. So you should just be aware that if it's colorless, you're not going to have absorption in the visible region, but you could still have ultraviolet. All right. One of the things we have to pay attention to is what wavelengths would we use. If we have the spectrum of what wavelength of UV light or visible light is absorbed, right, you're probably going to want to choose one of the wavelengths with a very high absorbance. So for example, I just put a line in so we could see that that blue purple peak, right, we're looking at a wavelength of maybe 430 nanometers, something like that, is appropriate. This is the absorption spectrum of chlorophyll A. Or if we wanted to look at the peak in the red region of light, right, we might be picking something around 660, 665 nanometers would be a very good wavelength because it's absorbing a lot of light at that whole region. And if you're going into Beer's law, picking an appropriate wavelength when you're looking at a spectrum is something you might be asked to do. I'm going to do a whole webcast on just Beer's law. I'll link that into here when I've got it made. Right. If there's more than one species more than one component in your sample, you might need to look at different regions. So if I'm looking at chlorophyll A, which is the green spectrum, and chlorophyll B, which is the red spectrum here, if I want to look at just B, all right, I might want to choose a wavelength of somewhere around, I don't know, 475 nanometers, where I wouldn't have much interference from chlorophyll A, would be very helpful. Or if I wanted to look at just chlorophyll A, I might look at a wavelength of maybe 670 nanometers, something like that, because I don't get a lot of interference from chlorophyll B at that point. Whereas if I were to choose something in the 440 wavelength, where I've got lots of A, A absorbs pretty well at that wavelength and B absorbs pretty well at the wavelength, it'd be hard to know which one I had. It wouldn't help me differentiate between them at all. So these are questions, things like this, that have been asked on the AP exam, so you need to be familiar with it. We don't need to go into great detail with any of these spectroscopic methods. Just as a quick summary, microwave is all about rotations. Some people like to think about the tray inside the microwave rotating, if that helps you. Infrared is all about vibrations, NMR is about nuclear spin, and UV-Vis is all about electron transitions. And in the end, that's what you need to know for this course. Have a great day.